Okay, I'm happy to see you again. Few but faithful, I guess. So we're starting our third journey, and as you read in Dan's message, it is independent from previous journeys. Of course, this independence is a somewhat fictitious independence. Mathematics is a unity. It's not a bunch of unrelated parts. It's one, as it were, seamless garment, and you could start from any place and traverse it. So we're going to start things, as it were, fresh, but of course, we're going to be talking about our old friends, say, natural numbers, which we encountered in the first journey and second journey, and we'll encounter in the third and fourth journey. But this is going to be a different path. And again, in the very beginning, of the first journey, I told you that mathematics doesn't really start with axioms. That it's not that mathematicians sit down, write a bunch of axioms, and then start deriving consequences. It's not what happens. Mathematicians discover theorems, and then gradually they put them together in the unified body, sort of connect them, and then they choose some minimal things which will let them prove these theorems. They call them axioms. And the choice is usually done toward the end of a formation of particular body of mathematics. Here we are going, today we are going to encounter axioms of natural numbers. And axioms of natural numbers were fully formulated at the very end of 19th century. Let me assure you, people have been using natural numbers many, many centuries before. And there were lots of number theory done dealing with integers prior to that point. But nevertheless, the story of formation of axioms is a marvelous and very important story. We shall see how it all sort of works in this course. And it again, sort of the attention to axioms starts again with our first and main example of axioms, Euclidean axioms. Because again, for centuries, it was the only example of axioms. Right? A lot of mathematicians learned axiomatic method while doing Euclid. The rest, they did somehow, without axioms. They were more or less rigorous approach, but there are no other examples of axioms. Axioms were sort of unique property of geometry. And we need to understand how axioms are formed, and need to learn to validate axioms. If you like, prove axioms. I know that it sounds, you say, Alex, you don't know what axioms are. Nobody proves axioms. Well, we will try. We will try to prove axioms. In some sense, if as we develop our discipline, computer science, we will discover axioms. For example, those of you who are a little bit familiar with C++ might have heard of concepts. You don't know what they are, but you heard of them. And what are they? They are axiomatic systems. They are collections of axioms. They are theories, right? And in order to understand how to use them, you have to understand how mathematicians use axioms. Otherwise, you will do silly things. So again, let us look at history. History is a very good guide for what we do. So we start with Euclid. Remember, he wrote this wonderful book called Elements. Well, actually, people are coming and coming. Wow, that's amazing. Guys, I would appreciate if we all come on time. This is not a corporate meeting. Uh, and when we look at Euclid, we observe that there are some strangeness at the very beginning. Actually, some historian of mathematics maintain that maybe he didn't write the very beginning. These things called definitions or common notions or postulates, axioms, properly speaking. Maybe somebody else wrote them. I don't believe it. I think that Euclid wrote them, but they look a little bit strange. And again, when you read Euclid with axioms as well as with theorems, he possesses this absolute minimality. He never explains to you what he means. You could ask Ryan, who has been reading Euclid. You have to yourself get to the bottom of it because he is very, very cryptic. There is no explanation why he separates, say, postulates from common notions, why there are two different groups of propositions. So again, maybe one day I'll teach a course on geometry, but this is not the time, so I'll go very quickly through the thing. There are some 23 definitions, and I'm sort of showing just two to give you an idea. First of all, the first one starts with this amazing, brief, and very profound thing. Modern mathematicians, of course, make fun of it. They say, what is this? Point is that which has no parts. Oh, but it's very, very profound. What does it mean? It means that the intersection of 2 points is a point. Right? That is, they cannot, since Euclid is built on intersecting things, lines, points, other figures. He tells that there is one unit which is minimal in terms of intersection. Right? And again, we skip lots of stuff and get to a notion of parallel line, which is going to be very important for us. So first of all, he states that two lines, if they're parallel, belong to the same plane. I mean, some naive people say, oh, parallel lines are lines which do not intersect. It doesn't quite work. These two lines are not parallel. You see? They do not intersect, but they're not parallel. So, and the second property, they're in the same plane, and you could go forever in whichever direction, they will not meet. There is no intersection. It's a very, very important definition. Then there are 5 common notions. And they are somewhat strange. They're strange because they're utterly non-geometrical. Right? Some of you, again, there are few of you who have my book, our book, and seen the definition of regular types. Well, the definition of regular types is pretty much stolen from Euclid. That is, the definition of equality which underlines, for example, programming, is the same as underlies geometry. Right? Sort of equational theories are the presupposition of everything. Again, another thing. Those of you who do not have the book, there are a bunch of copies, which I will be very happy to give you, free of charge, and you could obtain signatures from both me and Paul just for the asking. Right? There is no money involved. You just need to ask. You see, it's really sad as an author to constantly peddle your stuff. Oh, please take it. But again, sort of there you will see that these notions, these common notions which Euclid developed, apply to programming. Things which are equal to the same things are also equal to one another. Transitivity of equality. Right? Sort of, and when we go, we observe again the property of additions. If you add equal things, you will get equal things. Same for subtraction. Then there is the fourth thing, which is somewhat geometric, which tells you that congruence and equality, whatever that means, are fundamentally the same. And then the fifth property is again sort of saying, and some of you might say, well, he was ignorant, he didn't know about infinite sets. Well, he knew way more than you think. This does not apply to infinite sets, of course, but it applies to a whole bunch of these things. So if we rewrite them, we get beautiful. This is just a modern rendition. I didn't add anything. Modern rendition of Euclid's common notions. They apply all over the place, right? You know, be it integers, be it complex numbers, you know, lots of things follow these axioms. Nice stuff. So there are definitions. Then there are, if you like, fundamental presuppositions. That's what he calls common notions, which do not pertain to geometry. And then there are famous 5 postulates. This is the most famous 5 axioms in the history of the world. Of course, most people know the 5th. We will see why 5th is very important in a few minutes. So again, they are stated as phrases, if you like, as incomplete sentences, because what they say, what is possible. These are, if you like, instructions in your computer. What you could do, you could draw a straight line from any point to any point. Right? You could produce a finite straight line continuously in a straight line. It goes on forever. You could describe a circle with any center and distance, like that. Then all right angles are equal to one another. What does he mean? That if you have a right angle, another right angle, you could put one on top of the other and they will coincide. Right? And then finally, the famous 5th postulate. Again, this, as it were, probably the most sort of important proposition in history of mathematics in terms of its consequences. Right? We shall see that it affected all kinds of things. That if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than 2 right angles. Lengthy thing, but that's what it means. If the sum of these angles is less than 180, they will meet someplace. And you say, well, we could state it differently. Yes, you can. That's how he stated it. And you know, he is Euclid and you're not. So amazing stuff. They will meet. There is something from very early on, probably from about 2nd century BC, started bothering people. They thought that, well, I mean, other postulates, they're sort of elementary. First 4 guys, they're self-evident. They are, you know, basic. But the 5th one, we should be able to prove it, said they. And there starts a long and painful process, which goes for about 2,000 years, of attacks on the 5th postulate. Most attacks is an attack to prove it. Nobody actually, literally, nobody doubts that it's true, because it coincides with our basic intuition of space. And but people try, and there are sort of, you could write a book, yay big, on the history of sort of proving 5th postulate. There are some wonderful developments. Which people discover. That you could reduce Euclid's postulate to similar propositions, which are equivalent, right? So from 18th century, there is an English mathematician, John Playfair, who formulates that a given line at a point not on it, at most one parallel to the given line can be drawn through that point. That's the one you probably heard at school, if you had geometry at school, which is less and less likely. And those who take geometry at school probably don't hear about any axioms. But this one is relatively recent, it's 18th century, and that's commonly sort of presented now. Apparently another equivalent thing, that there exists a triangle whose angles add to 180. If you give me this, I could prove that, and the other way around. They're totally equivalent. We will see it's a very, very great importance. And then even more amazing thing, that there exist two similar triangles which are similar but not congruent. You say, come on, I mean, self-evident, take an equilateral, two equilateral triangles, they are going to be similar. Yeah, maybe not. We'll see. It's more tricky than that. This is an equivalent axiom. So people started sort of building up sort of all kinds of things. And I mean, very many famous people. Ptolemy tried. Proclus, one of the great sort of late medieval ancient philosophers, tried proving it. Amar Khayyam, yes?
So on the previous slide, was it the at most, chosen, on purpose, or why it's not exactly one?
Where?
First formulation. At most one parallel.
Because you could prove that there is one, as we shall see. Yes. People realized again, around 2,000 years ago, that there is a parallel line. The question is, are there two? Well, or more. Sadly enough, if there are two, there are three, and four, and five, there are a whole bunch. Well, eventually you will get to infinities. There are infinitely many. So, very good question. So Khayyam worked on it. He wrote these beautiful poems about drinking wine under a tree with having Nancy on your knee. No, this is Gilbert and Sullivan, but the same idea. Wonderful poet and great mathematician. And then, in early 18th century, came a remarkable book by Italian Jesuit Seccheri called Euclidus Vindicatus, Vindicated Euclid. What he does, and the book actually was published by American Mathematical Society, so still obtainable in both Latin and English translation. It's a remarkable book. So he sort of goes on and builds whole geometry assuming the contrary of fifth postulate. And in the end, when he produces so many bizarre theorems, he says, I clearly vindicated Euclid. Because the idea that all of this bizarre stuff could be true is really contrary to any sane mind. And it's true, yes, but so that was the state of the art. Very important book because, as we shall see, some important people read it very carefully. For example, Gauss. So here we come to a sort of very important point. Again, in Europe, every 100 years, there is a new mind shift. People start doing things differently, right? Sort of, if you look at European history, there are clear ideas. Sort of, you have sort of one age followed another age, and there is Eric Hobsbawm, a great British historian, actually talks to us about alternating long and short centuries. For example, 19th century is a long century. When did it start? Well, obviously in 1789. When did it end? Well, obviously 1914. It's a long century. 20th century, short century. When did it start? We already know, 1914. When did it end? 1991. Well, Soviet Union, kaput. So, and so on. I mean, we could find these wonderful alternations going very sort of back. And every century has a theme, right? And the same in mathematics. When we look at 17th century mathematics, people like Pascal and Descartes and Fermat, it's one mathematics, the one way of doing things. And then comes 18th century mathematics with Euler and Lagrange, very different way of doing things. In the 19th century, one thing which people start bothering, for example, in 18th century, all of these great people, people like Euler, who are towering figures, what didn't they care about? What didn't they care about? Axioms, foundations, right? Which was, they were a laughing stock of philosophers, because 18th century mathematics was full of fluxions, infinitesimals. And, you know, all clever people like Bishop Berkeley, there's this college around here named after him, were making fun of these stupid mathematicians who deal with infinitesimals. What are infinitesimals? I mean, they don't exist. So mathematicians didn't care about foundations. They were concerned about doing theorems out there. And then suddenly in 19th century, there starts a deep revisiting of foundations. Sort of, is it a house on sand? And, you know, there's a lot of activities which we shall see. And one of these activities that people start revisiting geometry. Sort of Euclid, which was taken for granted up till, say, 1830, is suddenly questioned. His axioms are no longer taken as if they are something which you cannot even discuss. They're absolute truth. And it starts with the following guy, Nikolai Ivanovich Lobachevsky. He was a provincial guy in Russia. Here what we shall see, starting from 19th century, there will be all kind of people from, you know, prior to 19th century, mathematics is done predominantly by French, German, English. This is it. Because other people are not participating in that. And then we shall see the same thing, by the way, applies to other things, like music. Music was predominantly German with some French. But suddenly in 19th century, there are all these other nations joining the club. And Russia, sort of as a result of 18th century developments from Peter the Great to Catherine the Great, joins Europe. So they have major university in St. Petersburg, major university in Moscow. Sort of they start there. Of course, they have Euler. But he doesn't leave a school. He leaves, 400 unpublished papers to be published. So Russian academic industry is doing very well for like 50 years after Euler is dead, because they still have these great papers to publish. But he didn't have students, or at least not in Russia. Lobachevsky, by the way, was not even born in Moscow and St. Petersburg. This is another example, sort of a very provincial person. He was born in Kazan. Probably never heard of Kazan. That's small, insignificant place at that time, populated mostly by Tatars, at the river Volga. That's where our friend Ryan is from, believe it or not. You never would have guessed that we have one person from Volga, and it's not Slava, was Sergei Petryan. Germans lived around Volga. Catherine the Great, attempting to civilize Russia, invited hardworking German farmers, like Ryan, to go there and plow the land, which they did very well. So thank you, Ryan. So he comes from that part of Russia, Volga, Kazan. They didn't have a university. He was the first person who actually attended, at around 1808, they start a university in Kazan. First university, he is the first student, eventually becomes a prominent university. There are several very famous people who graduated from there. One very famous writer, any guess? Make a simple guess, you will get it right. Do you know one Russian writer? Yeah, you got it, Tolstoy. And very famous Russian politician. Very famous Russian politician. Make a guess. Lenin. Yes, both Tolstoy and Lenin graduated from University of Kazan. And again, the first great Russian mathematician, truly great, graduated from Kazan. This is Lobachevsky. He was very fortunate. One of his Professor Bertner, was so happened before he moved to Kazan, taught some German guy called Gauss. So they shared teachers with Gauss. So he gets a decent education. But again, this is sort of, it's like getting degree in mathematics from University of Arkansas in 1850. Sort of, it's not a place where you become great mathematician. But he is very, very serious guy. He works very hard. He works so hard that he eventually becomes the rector of the university. And while doing this rectorship, president of the university, whatever he is doing, he wants to analyze Euclid. And he studies Euclid and studies Euclid and studies Euclid. And then he comes with the following, absolutely, this is sort of, nobody ever thought like that. At around, say, 1824, he realizes that he could build an alternative geometry. That, well, it's called Lobachevsky geometry because he built it, but he says, what if the world is different? What if you could have multiple parallel lines? Right? And he starts building this geometry in a systematic way, sort of he produces bunch of books, and publishes them. Around 1931, his book is published, and academic establishment in St. Petersburg say that he is an idiot, because nobody will ever doubt truth of Euclidean geometry. So he goes through a period of terrible rejection because he is sort of made fun of publicly by great people. Ostrogradsky, probably the most famous Russian mathematician at the time, student of Cauchy, sort of rejects it, says this is just nonsense. And then eventually, almost before he dies, he's sort of getting old, he is elected in Göttingen Academy of Science. Why is he elected in Göttingen? I told you about Göttingen. Who is in Göttingen at that time? Gauss is there. Yes, very good. This is the great place because Gauss was there. And Gauss learns the Russian and reads Lobachevsky and realizes how great it is. And the only recognition, actually a non-trivial recognition, was an election to Academy of Science of Göttingen, which, since if you are nominated by Gauss, I would be very proud of it. That's like, but again, everybody else ignores. So Gauss realizes full well, we will talk in a second about Gauss, and keeps writing books. For the next 30 years after his death, the work is utterly ignored. Then, of course, gradually it becomes famous. But at least he had a decent life, he had a job, he wasn't persecuted much, just made fun of, died poor. Well, could happen to any of us, will happen to many of us. Does, especially if you do stuff like that. I could prophesy that if you spend your time studying Lobachevsky, you're not going to be rich. He wasn't. So what does he show? He shows this amazing geometry. Again, I have to just give you a glimpse. I cannot cover it. But what he shows is that, as a matter of fact, there are no similar triangles unless they're equal. Because imagine, I will lie a little bit. This is not a correct model of Lobachevsky geometry. But let's take spherical geometry. Let's look at triangles on a sphere. What you would observe is if triangle is very small, it's almost like on a plane, on a ball. Therefore, the sum of angles is close to 180. As it becomes bigger and bigger in terms of it's much more than 2 pi, 180 degree. And in Lobachevsky geometry, it's the other way around. If it's a very, very small triangle, whatever it means, then it's almost 180. Bigger it becomes less and less. It's actually hyperbolic geometry. You have to, it's the opposite curvature to the sphere. And there are infinitely many parallel lines in a plane going through the same point, right? And there are all other amazing things. And they're totally different notion of area, and because triangles sort of, if you like, as they expand, their lines become, as it were, like that, straight lines. So their area become proportionately smaller and smaller as they grow. Funny stuff. Very, very strange stuff. So this is why many people make fun of him and say, this is madness, except Gauss. But before we get to, or maybe it's a good time to get to Gauss. I'm not going to tell you about Gauss. I told you about Gauss before. Still the same Gauss, but now it's a geometric Gauss, not number theoretic Gauss or probability theory Gauss. It's geometric Gauss. Apparently, Gauss does similar work. And from very early on, we shall see that he knew a lot of these results. So when Lobachevsky is published, he says, oh, this is genius. And for Gauss, you were a genius if you rediscovered what he discovered. But, well, let me tell you, it's a good thing. If you discover something Gauss discovered, you are a genius. Now, he, of course, absolutely refuses to publish. Why? As he writes to one of his friends, if we let it out, Philistines will have a day. Which is, all these stupid people will make fun of us, and that'll be the end of mathematics. We have to keep our mouths shut. These are not things to be discussed, right? But nevertheless, when Lobachevsky published, he is very, very happy. Sadly enough, well, there's just a quote from a very, very bad book. It's a very famous American book, which is probably the worst book ever written, but it's a good quote. Everything in it is wrong, except this quote. So it's not exaggeration to call Lobachevsky Copernicus of geometry. He turned things around. It's like saying that sun doesn't go around the Earth, right? Except in case of Copernicus, he was not the first. Pythagoreans, long time before him, believed that sun is the center of the universe. So, but in case of Lobachevsky, that was truly sort of fundamental breakthrough, and we shall see the consequences. So occasionally it's worthwhile quoting bad books. And here we come to a very, very tragic story. This guy is an example of somebody with nothing ever goes right. And first of all, we don't even know how he looks. You say, well, there are two stamps, Romanian and Hungarian stamp with his picture. Well, let me tell you, the situation was bad. When there was his 100-year anniversary of his death, they discovered that there was not a single extant picture existing. And there are these two countries which both want to lay claim, we'll get to that, on him, discovering there is no picture. So János Kadar called Georgiou Dash, these are bosses of corresponding country, and they agree that they'll just make up this picture. So we don't have any picture. So they made out the picture. Of course, there was constant. He is Hungarian, but in Romania, he is Transylvanian Hungarian, which is, he's a Romanian Hungarian. Well, he was, except at that time, he was Austro-Hungarian. There was one empire. It fell apart. Romania sort of still, at least then, I don't know whether it's true now, wanted to make claims that he was a sort of Romanian in spirit.
No, Bolyai, no. He is Hungarian.
But in 1960, there was, yes, so now apparently it's...
They call even the university in Cluj, Babes being Romanian, Bolyai being Hungarian.
But he was born in Romania, by the way, and he died in Romania. He was the son, you know, of a very great Hungarian mathematician, probably the greatest Hungarian mathematician up to that time, Farkas Bolyai, who was a good friend of Gauss. He was connected. And his father was a professor at Cluj, so it was sort of old, well-established. And they were strange, sort of, the family was Calvinist Hungarians. So Calvinist Hungarian and Romania, that's sort of, they were quite special. So in any case, he had this very precocious son who learned mathematics on his own, became quite adept at it, and followed his father's work. And what was his father's dream? It's easy to guess, to prove fifth postulate. So he worked, and his son decided to follow. His father actually became very concerned, and in some of his letters he writes to him that stop doing it, it will not lead to anything good. He was right. So János, however, suddenly had a sort of turnaround. He realized that instead of trying to prove it like his father, he is going to build, roughly like 2 years after Lobachevsky, he starts building quite independently alternative geometry, sort of. And he builds it, not as much as Lobachevsky, but it's not, you will see why. Because he builds a very nice write-up, sort of this geometry, and publishes it as an appendix to his father's book. And his father sends it to his dear friend Gauss. That's what you would do, right? You send the book, and you also say, note, my son wrote this very interesting thing as an appendix. Why don't you take a look? And that's where Bolyai tragedy starts. That's the answer from Gauss. I cannot praise this stuff. I did it all myself, long time ago. Right. Observe that in a different letter to somebody else at roughly 2 weeks after that, he says, oh, this young Bolyai is a genius of the first class. But he doesn't write it to Bolyai's father. So Janos is utterly distraught. You know, could you imagine that you did what you think is revolutionary work, and the greatest living mathematician at the time says, this is old hat. I have known it for about 30 years, and it's didn't bother to publish it. It's just nothing. Right? So he is devastated. By the way, Gauss did not lie. We have his diary. He did know it for about 30 years. Right? Sort of. The problem that writing notes in your diary does not give you publication priority, but not according to Gauss. Gauss used what American patent lawyers, if you sketch something in the lab notebook, that's good enough. So from his point of view, this all had 30-year-old results. It was known. So praising it, So Janos is utterly, he stopped doing mathematics. By the way, he's a cavalry officer, handsome guy, sort of one of the best fencers in Austro-Hungarian army, fencing, swords. First-class violinist, gives concerts in Vienna, a good shot, really good guy, totally unhappy. Never sort of figures out what to do with himself, stops doing mathematics. He keeps writing. When he dies, he leaves thousands and thousands of manuscript math doodling, unorganized. But he stops sort of attempting to communicate with mathematical community, and then he figured out what happened. He gets a Lobachevsky book, and he realizes what happened. You see, Gauss stole his idea and then invented this imaginary Russian guy, Lobachevsky, and published this stuff under this imaginary name to deprive Bolyai from his credit. It's a very sad story. He clearly becomes mentally unbalanced, and sort of, we'll see it. It frequently happens. Dies, again, in poverty, forgotten, abandoned. Nobody, at least Lobachevsky, is recognized by Gauss. His books are published. In the case of Bolyai, he dies in total obscurity. Clearly a very great mathematician. Right? This is why some people say Lobachevsky geometry, some people say Lobachevsky-Bolyai geometry. Some people even say Bolyai-Lobachevsky geometry, but that's less so. Now, that raises this remarkable question. Who is right? We have two geometries, Euclid and Lobachevsky. Could you raise the question of rightness? And let me tell you, here I'm not even asking your opinion, that from the point of view of Lobachevsky, Bolyai, and Gauss, the question was obvious. Only one of them is correct. That is, they were not, it never crossed their mind, that geometry was just a puzzle you do on paper. Geometry was a thing which described the universe. And if it describes the universe, it has to be either one or the other. And in case of Gauss, he wanted experimental confirmation, and he devised a plan for doing so. You pick 3 mountains in Germany, which are sort of high enough and far enough, but still visible to each other. So you put geodesic equipment on top of 3 and measure the angles right? Take the largest triangle you could make and measure the angles. If they're 180 degrees, then Euclid wins. If they're less, Lobachevsky wins. To him, it was, I mean, it never happened. He was, by the way, very involved in geodesic work. When they started doing sort of careful land measurement, he just, to facilitate it, invented differential geometry. People like Gauss do things like that. But it is quite clear that for them, mathematics was not just a game. It was a real thing. And the question, which one is true, was of paramount importance. Now, what happens within 30 to 40 years after discovery, and this stuff is published, several great mathematicians, you haven't heard of Beltrami, but you already heard of Poincaré and Klein. And Poincaré and Klein here are more important, I concentrate on them, show the following amazing result, that if Euclidean geometry is consistent, then Lobachevsky geometry is consistent. That is, not the other way around. That is, inside Euclidean geometry, you could build a model of Lobachevsky geometry. Okay? Let me quickly, very quickly, describe to you one of these models, Klein's model, because it's a little bit easier for me to describe. You take a plane, and you take a circle in the plane. You know what circle is, huh? And then you take a set of all projective transforms. You heard of projective transforms. I'm not going to define them. Projective transforms which keep the circle in place. The circle, it's not the inside, but the circumference of the circle in place. And doesn't mean in place that points of it do not move, but the circumference, all the projective mapping which maps circle into itself. For example, all the rotations would be, but it's more than rotation. And then apparently you demonstrate that the inside of this circle satisfies all axioms of Lobachevsky geometry. If you view points inside the circle as points and segments inside the circle as lines, you could clearly see that there are multiple parallel lines going through a point. Well, I am not allowed to do that, but I will just once. This is our circle. I know it's not very circle-like. This is one line. There's another parallel line, yes? There's the third parallel line. I mean, to this. More parallel lines. They're all parallel lines. You see what I'm saying? And therefore, sort of, this work by Poincaré and Klein demonstrated that, in some sense, if the world is Euclidean, there is a Lobachevskian world inside some of the thing. What happened? A break. I think, no, not break. Let me just finish with this. And then, sadly enough, comes the modern understanding. And it comes from a very great mathematician, David Hilbert. We'll talk about him after the break. And the remarkable thing that sort of what Hilbert decides is that we have to forget what is right, what is wrong. It's all the same. You know, if something is consistent, it's true. Right? In other words, geometry has no meaning. Points are no points. Lines are no lines. Planes are no planes. Once, with a group of students, he goes through Berlin train station. And, you know, this is Berlin, Germans, they're sitting there drinking beer. Right? So he pronounces these famous words that if we replace points, lines, and planes with beer mugs, tables, and chairs, it's all the same. It has no meaning. This is just a game. Did he believe it? As I'll tell you after the break is over, I don't think so. But he did say that, and it had grave consequences. See you in 10 minutes.